This is an engineering book of conversion factors. It is a handy dandy little book. I've had it for a long time. There are lots of them out there. Yeah, well, everybody else is the kind of stuff we used. I would carry my engineering handbook of conversion factors, and it would have the variety of conversion factors that are in here. And it is a nice, handy dandy book that's published. It also has capacity of bolted steel tanks. It has other pieces of cool information, knots and hitches. These were the kinds of things that you threw in your briefcase and took with you when you went to places to go out and do different work. So one of those handy pieces of information when you didn't have online and a smartphone. Okay, so where we ended yesterday was I was about to rework on the crank problem and doing a little bit more of these velocities and looking at this relative motion about the centers. And we were talking about the zero velocity location in order to get there. So we're going to revisit the crank problem, and I'm just going to draw the crank part from B to D here. And even though we've already found some of this stuff out, I'm going to draw my vector. This was my vector D. Here was my vector B. Yeah? To the left. Better? Okay. So we've got that VB, and I'm going to draw a line that's perpendicular to VB. All right, I'm drawing a line that's perpendicular to VB. And that's just going to be a reference line. Then I'm going to draw a line that's perpendicular to VD. Okay, so let me put things in. So there's my crank. This is from B to D. And so we've put in a 90-degree angle here. And if I came down to this part down here, we would see that this is actually a 40-degree angle that was formed by the other crank. Right, so this is going back to that crank arm that we were dealing with. So if I did this, I end up with a 40-degree angle here. And this was our beta that we've already found, okay? This is our beta that we've already found, and that was 13.95 degrees. So you can see that things are not necessarily drawn to scale. But I got my 13.95 degrees, but remember my rules. If that's a parallel line and that's a parallel line, then this is going to actually be beta. And that gives this to be our 53.95 degrees. And if I come back over here, and I know this is 40 degrees because of, again, using my geometry, I know that's 40 degrees. This is a right angle, so that's got to be 50 degrees. And then I can take my 180 minus 53.95 minus my 50, and that's going to give me my 76.05 degrees, which is going to be this angle right here. And I can get it a couple of different ways by doing this geometry. So this was back with my crank problem. But the key here is we can locate that center of zero velocity by drawing these two perpendicular lines. Okay, we can actually locate that 0 point by drawing these two perpendicular lines, and that's going to ultimately be this point up here where these lines intersect. So this way I could do it graphically to find that location, and this becomes point C. And how that simplifies my problem is that BC divided by the sine of 76.05, the length of that is going to give me CD divided by the sine of 53.95, and we know BD already because it was given in the problem. That's 8, and that was 7, or the sine of 50 degrees. So I can find BC, and I can find CD pretty quickly. And then my velocity at B is going to equal BC times omega BD, and that's our 62 radians per second. And then the velocity at C is going to be CD omega BD, and that gave us the 523 inches per second. And we had found omega previously, which is why I just plopped it in. But you can see how I shortcutted the problem considerably, because this is the same problem we've worked on for a while. But this is one way to locate that problem, that intersection of zero velocity. Okay, so we're going to kind of walk through some stuff here. So to determine the instantaneous center of rotation, there's 3 different ways. Okay? The first way is if we know VA and the angular velocity are known, you want to sketch the body showing A, VA, and omega. From A, draw a line perpendicular to VA. On the side of VA, which the velocity is viewed having the same sense as omega. So you're drawing VA relative to omega. And then we can locate the center on the line. And it'll be at a distance R VA divided by omega. So if we know VA and omega, we draw our sketch perpendicular with respect to, and this is kind of with respect to omega. We know that C is going to be on that line, and that the distance where it's going to be is just VA divided by omega. That's if VA and omega are known. We can do it again if the distance, so if the direction of A and B are known, points A and B are known, and they're different. So if we have the direction of the velocities at A and B are known and they're different, We're going to draw, sketch the body. We're going to still do that. We draw the perpendiculars. And it's to VA and VB. Okay. And the IC is where those two intersect. That was this condition right here. So because VB and VD were known, right? They were known. They were different in direction. We drew a perpendicular to VB through B, drew a perpendicular VD to VD through D, and where those lines intersected was our instantaneous location. Of the 2 points, A and B are known, and are both perpendicular to line AB. Okay? Still going to draw a sketch of the body, right? So we do our sketch. And we draw a line through points A and B, and another line through the tips of the vectors VA and VB. And then the C that we're looking for is located at the point where the two lines intersect. Okay, so it's going to be the point where the two lines intersect. I'm going to do a problem that does it this way. Okay, so let's do a problem that does it this way. So I've got a juggling club. And a juggling club kind of looks like this. It's kind of a funky thing. So there's my juggling club.
Oh, it's kind of like one of those things that look like bowling pins.
Yeah, it's kind of it's an extended long bowling pin, right? I've got a center of gravity that's kind of about there. And this whole thing is 20 inches. From here to here is 12 inches. We're going to rotate it around like this. It's going up with a velocity of 4 feet per second. Okay, it's going up 4 feet per second. And its rotation is 30 radians per second. So a juggling club is thrown vertically into the air. The center of gravity is 20 of the 20-inch club is located 12 inches from the knob. This is the knob, and that's where my 12 inches coming. Know that the instantaneous velocity is 4 feet per second upwards through the center of gravity. The angular velocity is 30 radians per second clockwise. We want to determine the speeds of points A and B and the location of the instantaneous center of motion. Okay, so we want to find So if I do this, I get VA is equal to VG plus VAG, right? And that is also equal to VG plus omega cross RAG. So I'm going to go ahead and get my vectors here. So omega is going to be 30K. This is equal to omega. This is VG is equal to 4 feet per second J. And this is my RAG. And I'm going to put it in feet. So this is 1 I. So if I do omega cross RAG, I'm going to get 30K crossed with 1 I, which is going to give me a negative 30J. And so if I do my VA is 4J minus 30J is going to give me a negative 26J. So this is going down at a negative 26 feet per second. And this is VB, this end is B. So if I do VB, this time my R is going to be the 20 minus 12. It's going to equal 8 divided by 12. Because it's got, this part is 8 inches and it's going to be divided by 12 to get me in feet. And I ultimately end up with this one being 24J because you're doing the same analysis. And if I look at VC is going to be I'm at a constant spot, so it's 0, and I'm going to end up with 4J plus 30K crossed with an X. I'm going to put in a question mark just so that we don't get confused. J. And that's got to equal 0, right? So, or that's not J, that's I. It ends up being in the J direction, so this is I. So I end up with 40 plus 30 question mark. And all of that's in the J direction. And I can solve for the question mark, and the question mark gives me 1.6 inches. A negative 1.6 inches. So it's going to shift 1.6 inches over here for my instantaneous center. But I could have done it graphically by that other method. So here's my line, right? This is my A and this is my B. My B was going up 24 feet per second. My A was going down 26 feet per second. And if I draw the line from these tips, okay, if I draw a line from these tips, that shows where the instantaneous center is. So I could have done it graphically as well. And in some case that makes it a lot easier to do. Now, one key point about instantaneous centers, okay? Instantaneous centers of rotation can be used only to determine velocities. Can only be used to determine velocities. We can't use it for acceleration. We can't use it for acceleration. Okay? All right. Yeah. VC is 0 center, and it ultimately equals 4 plus 30 question mark, which is going to give us our distance. Because we're using VC to find the instantaneous center in this case. Nope. Well, the numeric value for the instantaneous center is 0. That's the whole point of the instantaneous center. Okay. All right. So I've got this weird tape dispenser. And it's more likely a measuring tape dispenser. It's attached to a rod. Here's the core of the tape dispenser, and then there is the tape on the tape dispenser. Okay? The tape on the tape dispenser is coming off, and we're pulling this thing up at a velocity. This is on the A side, this is the B side, and we have a velocity going up. Okay, we've got a spool of tape is known, and its frame assembly are being pulled up 80 millimeters per second. So this is going up at 750 millimeters per second, which is going to be 0.75 meters per second. Knowing that the radius, we have a radius of the spool, okay? And the radius of the spool is this. So the radius of the spool is equal to 80 millimeters. The spool has an angular velocity in the clockwise direction, so we're rotating it around like this, of 15 radians per second. And so this is the instant shown. The other thing that we know on the instant shown is we get the thickness of the spool, the tape on the spool, and that's 20 millimeters. So the radius of the spool is 80 millimeters. The thickness of the tape around the spool is 20 millimeters. We want to determine the instantaneous center of rotation of the spool and the velocities at points B and D. B is here, D is there. Okay? So one of the things we know, so if I look at my spool, there's VB, and even though VA is listed as over here, we know that our center of our spool is moving up at VA, right? So one of the things I already know is that my instantaneous center is going to be on this line. Okay, it's going to be on this line. And it's probably going to be some point along here. So I'm going to give myself a marker here, and I'm going to give myself a little distance x.
Can you write X's?
That x is a distance.
You have like X on the line, but you also.
I just have a mark on the line.
Okay.
I can make
What's
it.
that X1 right there?
That's telling me that this is the distance between the center of my spool and my instantaneous center.
Okay.
We just don't know where that is. Okay, we don't know where that is. And that we're going to mark as C for my instantaneous center. Okay, we okay with that? So CB, the distance from C to B, we know the distance from here to the spool radius is 80. We know the thickness of the tape on the radius, but we don't know that distance X, and that gives me my C, that gives me the length for my CB. VA, because that's known. Omega is known, but my R is not known. So I can just do VA over omega gives me R. Turns out that gives me 50. So my X is equal to 50. Turns out that CB then is going to equal 100 minus X is going to equal 50. This is one of those cases that if you go on Chegg, you say, okay, I see 50, but where did the other 50 come from later? And that's where the other 50 comes from later. And this is because this is my 750 divided by my 15. This is still in millimeters. This is still in millimeters, so that I have that. So my velocity at B, VB, is just going to be the length of CB times omega, which is 50 times 15. It's going to give me 750 millimeters per second going down. And then if I want to do D, okay, there's 20, 80, and that's 50. So CD, so V at D is going to be CD omega. And that's going to be 130 times my 15, which is going to give me 1950 millimeters per second. And that's going up. And my instantaneous center of rotation does not necessarily have to be on my object. So let's look at problem. We're doing problem 84. I've got a velocity of my conveyor belt. I've got an object that's rotating. It has a 1. And here's C, here's A. When omega is going that direction, 2 radians per second, and the belt is moving at 8 feet per second. I want to find IC. Well, RIC, yeah, the velocity is 8, my omega is 2. That's telling me it's at 4 feet. So this is 1 foot, this is 1 foot, and to get at 4 feet, I have to add 2 feet above. Here's my IC. And then if I want to find VC and VB, VC is just going to be R omega, except now I've got to do, there's my 2 plus 1 is 3 for my R, and my omega is 2 radians per second. This gives me 6 feet per second. If I want to do B, I'm just doing my 2 feet times my 2 feet, and that's 4 feet per second. So finding that instantaneous center of rotation speeds up my problems considerably.
How did we know that the 8 feet per second related to the instantaneous center? I would have guessed that would have been V sub A.
That is V sub A. But I want to find my instantaneous center there, and that's perpendicular. And that first set of conditions, if I know VA and I know my omega, I can find the distance RC.
So it's saying RC means like if you're going this fast and the wheel is this big, this is how much feet you'll cover.
No. RC is the distance
RIC right there.
that my instantaneous center says that the velocity at this point is 0,
Yeah.
pretty much. And it helps me figure out the velocities. Okay. That said, we can only use that instantaneous center to help us do with velocities. It doesn't help us with acceleration. Okay, it doesn't help us with acceleration. So now we gotta start looking at acceleration. And we gotta start expanding this motion to acceleration. So we can do dVB dt, and it's gonna be my derivative of VA dt. Plus, remember we're doing this with a relative VA, the velocity of V with respect to A dt, right? These right here are measured with respect to the fixed axis. And thus, hence, they are absolute accelerations. Okay, so if I start with this, so I'm going to use figures from the book so my drawings don't get funky. All right, we've got our velocities A and B. We're going to do our general plane of motion. So I've got curving, I've got the other plane of motion, and we've got these two are absolute accelerations. But I can break it up into parts, right? I can break it up into my translational acceleration. And I can break it up in my translational acceleration. But then things get really mucky, right? They get really, really mucky when I have to look at my rotational. And when I look at my rotational, I'm going to have a normal component and I'm going to have a tangential component. And remember, this is the relative acceleration between A to B. So I'm going to have a tangential and a normal component of my acceleration. And essentially what happens if I do my vector analysis I've got my vector A, and I take the tangential component of AB and the normal component of BA, and I should get, adding those vectors head to tail, I should get AB. So I can get there. So because it appears in an arc, make sure I'm not losing. Brandon, can you still see things and we didn't drop from here? Okay. So I get an absolute acceleration. And so what we know about vector AB, or the acceleration of BA, is that there is a tangential component and a normal component. And we've seen so far that if I do this, I'm going to get my angular acceleration, BA, and this is for my tangential component. And we know that we can do BA for my, oops, this is my normal component. And this so far is magnitudes only, because these are vectors, and so they have vector quantities, and we have to worry about that. But we know this one comes from and we know this one comes from and there's a negative in there. So we end up with our equation. I'm going to double check, make sure I haven't screwed something up. Yeah. We're going to start with a rolling disc. There's the center of gravity. There's A. It's rolling about there. Omega is going to be 6 radians per second, is 4 radians per second squared. And R is equal. Determine the acceleration at A with no slipping. The general equation is my acceleration at B is going to be equal to my acceleration of A plus alpha crossed B to A minus omega squared RBA. So the first thing I want to do here is, I'm going to rewrite this equation so I have it straight. This is going to be AG plus alpha RBA minus omega squared RBA. First thing I got to do is I've got to write this. Well, let's find AG first. So AG is just going to be my 0.5 times 4, because this is my R alpha. So it's going to give me 2 radians per second squared. And because I'm going this way, my right hand rule is going to have it come out of the paper. That's going to be a negative 2K. Oh, I did it this way. Sorry. Got a negative 2I. Because that's going this way. That's this one. That's my AG. So my G is going that direction, so it's negative 2I, because I'm rotating this way. RAG, which is what I'm going to need, because this is now my direction there, that's going to be a negative 0.5J. Alpha is going to be 4K. And my omega is right there. So what I end up with is minus 2I plus 4K crossed minus 0.5J minus omega squared minus 0.5J. You end up with negative 2I plus 2I minus a minus 6 squared 0.5J. Play with all of this, and it gives you these cancel out. It gives me 18J feet per second squared. Now, for these problems, it makes it a heck of a lot simpler if you remember a couple of things, because I didn't have to go to my matrix to do this. So you remember that I cross J is going to equal K. J cross K is going to equal I. K cross I equals J. And if it's J cross I, that equals minus K. And if it's K cross J, that equals minus I. And I cross K is going to equal minus J.
So it's basically like if you take 2 out of the 3 variables and multiply them, they will always equal the other variable, but it depends on which order it's in.
Mm-hmm.
So,
Yep.
okay.
And this is the right-hand rule. And then if I do I cross I, which is equal to J cross J, which is equal to K cross K, which is equal to 0. It's just helpful to remember that, because when we end up working these problems, we're going to end up with these kind of cross terms. And I don't have to go to the whole matrix to figure those out, because now that's like 0.5 times 2 gives me 2. I've got K times J, that's going to give me an I, but I've got a negative times a negative, that gives me a positive 2I. So that's just something to remember as we work through this. So we're going back to our crank problem, except now we want to determine, so this is back at the crank problem. We want to determine the angular acceleration of the connecting rod BD and the acceleration at A and the acceleration AD. So we're gonna start with the part that went from A to B, because I gotta get this acceleration to do the BD part of the crank. This is 3 inches. So the acceleration AB is just gonna be A omega AB squared, and alpha AB, we're told in the problem, is going to be 0. And we found omega AB early on as 209.4 radians per second. Since the crank rotates about A with a constant AB, I can get rid of the acceleration AB and just give me my AB, which is now going to be 3 divided by 12 to get me into feet. 4 squared is going to give me 10,962 feet per second squared. Remember, just so that we keep this is 40 degrees. And this is my acceleration, AB. And now if I do my crank BD, okay, my crank BD, and we had and this is our velocity B, we had our velocity D, and we had this angle, and we already know that angle because we've kept it, which means I'm gonna get a velocity in this, or an acceleration in this direction, and I'm gonna get an acceleration in this direction. I can rewrite this as its components, where the translational, where it's going to be related to AB. So it's going to translate that way. But now I've got to worry about the rotational. And the way I'm going to worry about the rotational is I'm going to do our omega BD. So I'm going to have an alpha BD. I'm going to go ahead and put this thing in here so that I can have an AD tangential and an AD normal. And that's the rotational side of my crank problem. And we found omega BD earlier, we found beta earlier, so beta is 13.95 degrees, omega BD is 62 radians per second. I'm going to need ABD, BD tangential. And this gives me BD omega squared. It's going to be my 8 over 12 because this was an 8-inch bar. 62 squared, which is going to give me 2,536 or 2,563 feet per second squared. And then I get BD alpha, which is going to give me 0.667 alpha. And we don't know that yet. It's not something we know yet. We also know that AD is going to be ADI from our original drawing. Again, this is something we don't know yet. All right, but I got an angle here, so I'm going to do some things for this one right there. So I'm going to get my ABD normal is going to equal a negative 2563 cosine of my beta, which we already know. I'm just going to do it to make it easy to write on the paper, plus 253 or 2563 sine beta j. And my alpha beta d tangential is going to be my 0.667 cosine, and we've already found that 76.05 degrees. There's an alpha there. I kept, in my notes, I kept having to go back and rewrite the alpha, put it back in there. Alpha j. And AB is equal to minus 10, 9, 6, 2 cosine 40 degrees I minus 10, 9, 6, 2 sine 40 degrees J. So I've got those three. And I have alpha, so I got my alpha B, got my alpha BD. Okay. So what you want to do at this point is you know that alpha D is equal to AB plus ADBT plus ADBN. I have an X component and a Y component. So by using the X components, okay. And one of the things that I know my Y component is AD is equal to 0 in the J component. Okay? We got AD is equal to 0 in the J component. Which means that if I use my X component and my Y component, I get two equations. I can simultaneously solve, and I get AD is equal to 9,290 feet per second squared, and I get alpha is equal to 9940 radians. Okay, so everybody see, because for the interest of time, I'm going to shortcut it. I've got all three of these vectors, there they are. Vector AD is just equal to AD in the I direction plus 0 in the J direction. So I can get two equations, two unknowns, and I can simultaneously solve for AD and alpha. Trying to keep my notes nice and straight. All right. Now, in my notes, I have 1, 2, 3 problems that I've solved. But in the interest of time, I want to get you through this chapter. So I'm going to skip that for right now. And we're going to work through what's left of the chapter so that you have the theory down to be able to get the homework problems done. Because we're going to complicate things one more time. Because so far all we've dealt with what we've done is we've got a fixed component system. So that's fixed, right? And then we had a component system for our object that was allowed to move. Except it was only moving in a translational form. Now what we're going to do is we're going to allow not only to translate, but to rotate. You knew it was coming, right? You could have bet money that we were going to do that, right? You could have bet money. Now, I will tell you that the equation is going to look god awful, but in practice, it's really not that bad. All right? The equation is going to look god awful, but in practice, it's not that bad. So, kind of thinking through this, all right? Kind of thinking point. Here's our shift and our change of angle to get the rotation around. We're going to use a big omega to help describe what's happening as it goes around. Okay, we're going to use that big omega to account for our rotating coordinate system. So what happens to us is this, is that RBA now is going to be an XB in the I direction plus a YB in the J direction. And when I do my derivative of RB, because remember that RB is equal to RA plus RBA, we're going to end up with VB, which is equal to VA plus now our DT of XB in the I direction plus YB in the J direction. But constant, so we end up, when I take this term, DT I plus DYB DT J plus XB D plus Y DJ DT. DI DT becomes d theta DT, and that ends up being omega in the J direction. Similarly, dj dt is equal to d theta dt, and that's in the minus I direction, and ends up being minus omega I. This ends up being omega cross I, and this ends up being omega cross J. Which essentially becomes VB is VA, which is equal to, oh, no, that's not equal to, that's plus omega cross RBA plus the velocity of VA XYZ. So let's take each component. VA is the velocity of the origin of the moving reference. VBA of B with respect to A as measured by an observer on the moving reference. Omega is the angular velocity of the moving reference. And RBA is the position of B with respect to A. Okay, again, in the interest of time, we're going to move through all of this and we're going to get acceleration. So we're going to do the derivative of this and get acceleration. And we can work through the same analysis to get acceleration. So we're going to get acceleration. Now acceleration is going to look like this. AB is equal to A plus, where that's my time derivative of my angular acceleration. Or, so let's write through this. So AB is the acceleration of B measured from the fixed frame. Acceleration A is the acceleration of the origin of the moving frame. ABA and VBA is the motion. Oops, yeah, there we go. Motion of B as measured by an observer on the moving reference. This is the angular motion of the moving reference. And RBA is the position of B with respect to A. So like I said, it looks awful. It looks awful, but it really works out that it's not that bad. So I'm going to do a couple problems to kind of help you out here. So here's I've got a disc. The disc is rotating around Z. We have a slot where the ball is moving in our slot here. And what we want to find is, we want to determine, so we've got a disc with omega, I have the radius of my circle, and I've got that position. So first, let's determine the velocity of the ball. The velocity of the ball is going to equal the initial velocity plus okay, from the problem, we can start writing some things down. So I've got, in this case, here's the good news. In this case, we've got just the disk that's moving around, so I'm not moving my origin. So v of the origin and acceleration of the origin are both going to be equal to 0. We're given omega as 6 radians per second, and that's in the k direction. And we're given omega dot is equal to 3 radians per second squared in the k direction. We need RBO, and we've cleverly oriented it so that's 0.4i. Okay, and the problem tells us that the ball has a velocity, so my ball relative to my origin and the acceleration of the ball relative to the origin, we're told in the problem, are 0.6 and 0.15, and this is going to be in the I direction, and this is meters per second squared. These are given. These are on the diagram. Same with that one, it's on the diagram. So the problem gives me a whole bunch of stuff. Well, that's great, because now v of the ball is just equal to, I'm going to do my 6 outside. I'm going to do my RB outside just for keeping things straight. And I'm going to do my K cross I. So I've got that one straight, plus 0.6 meters per second in the I direction. 0.4 times 6 is 2.4. That's in the J direction. 0.6 in the I direction. This is in meters per second. Since I usually have I in front, I'm just going to change things around. Voila, I have the velocity of the ball. To do the acceleration of the ball, that's AO plus omega dot cross RBO plus omega cross omega cross RBO plus 2 omega plus VBO plus ABO. We already know this one from up here, so that makes life a little easier for us. That term goes to 0. Okay. This becomes we're going to put our 3K cross 0.4 I. Then I get 6K cross 2.4J, because that came from up here. We already figured it out. I do times 6K cross 0.6J plus that one is 1.2J. No, I'm sorry. That one is 0.6J. I was writing down my in the middle arithmetic. And if you clean all that up, you get minus 14.2I plus 8.4J. So it looks awful. The big key is getting all the different components out. So we'll get another one, do another one to help you out. We've got a swing bridge.
it's a bridge that turns like
Yep.
this. Why do they make those?
So boats can cross.
So this one boats can cross, but the other place, the place I see it more often is in a train house. In a train barn. Train comes in on this, it rotates around so you can put an engine into a bay to work on it. So most of them I see are on same kind of
Same principle did one in real life, so I was just confused as to like why someone would build that.
oh, I've seen several of them.
But then common sense over.
It just depends on the
Same concept as a drawbridge.
yeah, just a different application. And like I said, I've seen them in a train barn more than any place else. Train barn's a better place for them. So we're given a swing bridge. Now, here's the trick on this one, and you'll have to pay attention on the homework just to make sure, because this is not how I would set up the problem, but this is the way the picture's set up. I would have set up the problem that the man that we're worried about is walking on the x-axis, okay? They set it up that the man that we're worried about is walking on the y-axis. Whatever, whatever. So I've got and then I'm going to swing this around. So given our swing bridge and given the information that we're given, okay, first thing that we're to constant velocity, angular velocity of 5 radians per second. Okay, that's equal to 0. Yay, we've simplified the problem dramatically right off the top. We're given that d, the distance that the person has walked is 10 feet. And at that point, they're walking at 5 feet per second. And acceleration is equal to 2 feet per second squared. We want to determine the velocity and the acceleration of the man at the instant given. And this is, they tell us that this is relative to the roadway. I can't write now. That is relative to the roadway. So what I do for these problems is as follows. I go, all right, I'm going to write down given what I've got. I've given velocity AO, okay? That's my man. This is, with respect to this picture, is going at negative 5J in feet per second. RAO is a negative 10J in feet. And AAO is a negative 2J feet per second squared. We're given omega is equal to 0.5 K, and omega dot is equal to 0. VA and AAA are equal to 0 because I have a bridge and my origin isn't moving. So VM is now just going to be 0.5 negative 10 K cross J minus 5J. That's going to give me, that works out to be 5. And this gives me a 5I minus 5J. AM is going to be, I get 0.5 times 5 K cross I plus 2 times 0.5 times 5, and that's a negative 5 K cross J minus 2J, and that works out to be 5I plus 0.5J. So again, it looked horrible to start. The equations look messy. but they actually simplify out fairly nicely. That gives us all of the theory and stuff that we've had for chapter 16. I have 3 more problems for chapter 16 that I've worked out. But I am sure brains are full.
My brain's full now.
Yeah, I'm sure brains are full. We'll start chapter 17 on Monday.
How many chapters are there in this class?
I gotta get to 19. I have to get us to 19.
Okay.
And we'll start 17 on Monday. We should, and actually 17 goes really, really fast because I gave you all of the homework for chapter 17.
So so this is the end of the 4th week, so we're 2/3 of the way through the
Right.
course. Then we have 2 more weeks, so we'll do 17, 18, then you'll hit 19, and then we'll do the final.
Pretty much.
Okay. Do you think 19 will be on the final?
19 will definitely be on the final. Yeah. Through chapter 19 will be on the final. I'd like to get to 3-dimensional motion, but tough.
Yeah. Well, just a little.
Yeah, but chapter 17, I went through. Chapter 17 only has like 6 sections in it, and it's moments of inertia, and you guys can already start. I already released the homework because the very first part of chapter 17 is calculating moments of inertia of objects, which we've done in statics. You've done it in calculus. You've seen it. You know, it's just kind of a refresher on moments of inertia. I think I only assigned 4 problems total for doing it, just to get you back into practice for moments of inertia. And it's just to review the parallel axis theorem, that kind of stuff. So if you want to start chapter 17, you can. I do have chapter 17 due. I have it due on Friday night so that the extra credit and stuff can go in by Monday of next or the following week. Because and at this point, probably for chapters 18 and 19, I won't assign any follow-up for points, just because we won't have time. It would run out to after the final date. And my plan for the final is I'm looking at FE style questions that you'd see on an FE exam. So I'm looking at doing, probably the final is probably going to, in order to be able to be done in a 2-hour block, in order to be able to do that, I'm probably looking at like 8 questions, 4 of which would be FE type questions, and then 4 would be like working problem type questions. So 4 would definitely be multiple choice, and then 4 work out the problem.
And you said it'll be open book, open note, right?
Open book, open note. Yep. Yep.
Almost there, guys.
So have a good weekend.